The two-period overlapping generations model with growth from chapter 3.4 of the book Public Economics. Hello and welcome to the fifth video on the chapter 3 of my book Public Economics on the overlapping generations model. So far we have studied the competitive economy, the decentralized economy, and the central planners problem in the case of no growth. And today we look at the case with technological growth, with labor augmenting technological growth to be more exact. So why is this an important problem in the overlapping generations model? We often use the overlapping generations model to study questions of pensions or of debt. Now, in both cases, the growth rate is crucial. So look at the pension system. Modern pension systems are pay-as-you-go pension systems. So the current workers pay to the current old. And when the current workers get older and retire, they will again get a pension from the workers in, let's say, 10, 20, 30 years. So I hope that I will get a pension from you in 15 years when I am retiring. Now, the return on my pension, on my contributions today, and my pension in the future, of course, depends crucially on their growth rate. So if the economy is growing at a fast pace, then you in 20 years will contribute a higher amount to the pension system, and I will receive a higher pensions. If not, well, then the return on my contributions today will be low because I will get lower pensions in 15 years. The same holds for the debt problem. So today we have Corona and we have to accumulate large amounts of debts in the industrialized countries and all the other countries. And one day we have to repay it. And we also have to service our debt. So this, of course, is less of a problem if economic growth is high and we have high tax revenues in the future to repay our debt. Now let's get into the overlapping generations model, and therefore I would like you to download the teaching slides on chapter 3 of my book from my homepage. And they should look something like this. Public Economics, Macroeconomic Perspective, chapter 3, the overlapping generations model. And we get into chapter 3.4, the two-period overlapping generation model with technological progress. So this is on slide 57. So we use the same structure that we analyzed in the preceding sections. So we have a two-period model. In each period, there's one young cohort and one old cohort. And in the next period, the young cohort becomes the old cohort and the old cohort dies. And a new cohort is born. The population and the number of young cohorts grows at the common rate n, so that the number of young people, NT, grows by n, as in the first equation on slide 57. We assume that only the young generation, the young cohort, is working, supplying 1 unit of labor, so let's say 40 hours a week, and total labor supply therefore is equal to the number of young people. In the first period, the household consumes C1T. In the second period, when they are retired, they consume C2T plus 1. So the superindex 1 and 2 is the age, workers and retirees, respectively, and the subindex T and T plus 1 are the time periods. Lifetime utility is additively separable in utility at young age and at old age. Sorry. And your instantaneous utility of consumption is logarithmic. Old age utility is discounted with the factor beta. So lifetime utility is presented in equation 36. Now we introduced exogenous technological progress, and we introduce it in the form of labor augmenting technological progress, so that our labor NT is multiplied by the factor AT, the labor productivity AT, which grows at the exogenous rate gamma as given in equation 38. So for our Cobb-Douglas production function 37, it doesn't really matter if we introduce it as labor augmenting technological progress or as capital augmenting technological progress. But if we have, for example, substitution elasticity between capital K and labor L that's different from 1, then we can only use labor augmenting technological progress, as you might know, because then only this kind of technological progress is in accordance with the long-run features of our economy, so that we have growth, but no trend in the savings rate. So savings rate goes not above 100% or below 0% or something like this, but there's no trend in the savings rate. And this is only in accordance with labor augmenting technological progress. Therefore, the household budget constraint changes to equation 39. So the household gets labor income WAT and spends on consumption C1T and savings ST. Notice that there is no super index with savings because only the young people save, so we can drop it. Now we have introduced the wage rate here, WT, as the wage rate per efficiency unit 80. So the household works 1 unit, 1 has aggregate efficiency 80, and as a consequence, he gets the wage WT and labor income WT 80. Now, we do not really observe this wage rate per efficiency unit. So I couldn't tell you what's the wage rate of my efficiency unit. I don't know how efficient am I. We observe hourly wages or wages per unit of time. In this case, our budget constraint would look like the third equation. Savings ST is our wage rate per unit of time, tilde WT minus consumption. Now we would like to specify our model in stationary variables, otherwise it's difficult to solve for models. So we would like to have parameters, variables that do not change over time in the steady state. And therefore we use the new variable WT, which we define as the ratio of the wage rate per unit of time, tilde WT, divided by aggregate labor productivity, AT. And then our budget constraint, which you might be familiar with, ST is equal to tilde WT minus C1T, becomes equation 31. Now, in the second period of life, when we are retired, in the simplest model, we do not get a pension. This is left for analysis in chapter 6 of my book. We just have savings, ST, and we get interest rate RT plus 1 on our savings. So we consume all our income, which is savings plus interest, and therefore consumptions in old age C2 is equal to the right-hand side of equation 39b. We can substitute 39a and 30b, get the lifetime utility and maximize, lifetime budget and maximize lifetime utility 36 with respect to our intertemporal budget constraint, and derive optimal savings, which in the case of a logarithmic utility function is just a function of wages. So that's the neat property of log utility here in our overlapping generations model. The income effect and the substitution effect of the interest rate RT plus 1 just cancels, so that savings are just a function of WT. Firms maximize profits, and profits are production with the help of capital K and labor AT&T, effective labor AT&T, minus wage costs, WT AT&T, minus interest rates costs RT KT, minus depreciation delta KT. So therefore, we get that the wage per efficiency unit WT is just the marginal product of effective labor, AT&T. And when we define the capital intensity lowercase k as uppercase K over AT&T, so our KT here, lowercase kt, is equal to this expression here, to this fraction, uppercase kt over AT&T, we can describe the wage rate per efficiency unit as a function of the capital intensity, lowercase k, and also our interest rate, which is equal to the marginal product of capital minus the depreciation rate, is described by a function of the capital stock kt. So we assume here, of course, in the derivation of equation 40 that we have competitive goods and factor markets. And also, therefore, the Euler theorem holds that total production is paid out in the form of wage and interest income. So profits are zero in equilibrium in our model. Now, the capital market equilibrium, as we've learned before, total savings of the households, of the young households at the end of period T, which is ST individual savings times the number of people NT, are the beginning of period T plus 1 capital stock, and then the period T plus 1 capital stock is used into production over the period T plus 1, together with the new labor supply, which is efficiency AT plus 1 times number of workers NT plus 1. So we can substitute our solution for optimal savings into the capital market equilibrium here and derive the second equation on slide 61. So NTST is equal to KT plus 1. Divide this equation by the number of people NT in period T, of the number of young people, of workers in period T. And then we just get a dynamic equation in the capital intensity KT. So, and 41 describes our new dynamics. For what's new in this model with exogenous technological progress, well, here we have the growth rate gamma, which in the former model without technological progress is simply equal to 0. So this term 1 plus gamma just drops out in the case without growth. Otherwise, it's identical. And of course, we also have, in this case, that A is equal to 1 if we have no growth. So in steady state, the capital stock is constant. So we have KT plus 1 equals KT, or rather our capital intensity here is constant. And we can solve this equation 41 for the capital stock and come up with the first equation on slide 62. The capital stock per capita grows at the rate gamma, and total capital stock grows at the rate gamma plus the population growth rate n. And we can derive the interest rate from our steady state capital stock. So the steady state interest rate is simply given by substituting K into the marginal product of capital here, and we get the right-hand side. So this is the way we introduce labor augmenting technological progress AT into our model and also have exogenous growth. All variables that we have considered now the real interest rate and the wages are constant in our model because our capital intensity is constant. Per capita variables like consumption and savings, they all grow at the rate gamma in steady state. Now, how does this consideration of technological progress affect our result on the golden rule, our modified golden rule. Let's look at the resource constraint of the central planner for this rule, for this reason. Now, our resource constraint is basically the same. On the left-hand side, we have total production and we have capital. And in contrast to the previous section, we now introduce depreciation delta. So at the end of the period T, what's left to distribute, what's left to allocate for the central planner? He started the production with capital KT at the beginning of period T, but at the end of the period, only 1 minus delta times KT is left from this capital stock for the allocation on consumption and investment. Over the period, he has produced with capital stock KT and labor NT and effective labor AT NT. So total production is F of KT AT NT. So production and depreciated capital stock, he can use it to either allocate it to the investment in the new capital stock, KT plus 1, or on consumption. And the young households in period T consume C1T. So NT C1T here, that's the consumption of the young people. The old people, they have number NT minus 1. These are the young people of the previous period, T minus 1, and they consume C2T. Now, if we divide this equation by AT NT, by effective labor, we get an equation in the capital intensity, KT, which is much more convenient to handle because KT is a stationary variable. And we just derive the second equation here, 1 minus delta times KT, our depreciated capital stock per effective labor, plus production per effective labor, F of KT, is equal to next period capital stock. So here we have to consider that the next period capital stock, the total capital stock has to be allocated to a higher number of people, which grows at the rate 1 plus n. And it's also, in terms of efficiency units, the efficiency units also have grown by the factor gamma, our growth rate. And we again define our total consumption per young worker, CT, as in the previous section. So the consumption CT, lowercase ct, is defined as total consumption of the young plus total consumption of the old divided by AT/NT. Now in steady state, this equation here, as you can see, if KT is equal to KT plus 1, then a couple of terms cancel, and we are left with the equation f of k is equal to n plus gamma, gamma plus n times gamma plus delta times k plus c. So that's our resource constraint in steady state when capital intensity KT is constant. Now when we differentiate this equation with respect to k, we get that the marginal product of capital F prime minus the depreciation rate delta minus n plus gamma plus n times gamma is the effect of higher capital intensity on consumption. And we have shown that the economy is dynamically inefficient if this derivative is smaller than 0, because then if we reduce the capital stock, of course, the reduction of capital stock can be given as extra resources to the current alive generations, so they benefit, they have higher consumption. And in the next period, we again, in the new steady state, keep capital constant, capital intensity constant. And because capital intensity has declined, consumption must have gone up if this derivative is smaller than 0. So all generations benefit. This is not the case if the derivative is larger than 0. And for this reason, let's assume we increase the capital stock. This means the current generation must save an additional amount of capital for the next period, so they would suffer during the transition. And here now our condition for dynamic inefficiency is now that the real interest rate, which is the difference between the marginal product of capital minus depreciation, now has to be below the population rate plus the growth rate and this interaction term here, n times gamma. So in comparison with the case without growth, where gamma is equal to 0, this condition is more likely to occur. So let's look at a typical value for the interest rate R. In many dynamic general equilibrium models, this one is calibrated to a value of 4% annually. In the United States, the population growth rate is about 1%. So without growth, this is the United States is dynamically efficient. Now, if we consider growth, so gamma is not equal to 0, but let's say 2 or 3%, well, for this calibration, for this particular example, this equation does still not hold, and our economy is dynamically efficient. So R, let's say, equal to 4%, and 1%, gamma 2%, 3% is lower than 4%, and our economy is dynamically efficient. This is the case that has been emphasized by Piketty in his book 2014, Capital in the 21st Century. So his argument was basically the following. Well, the capitalists, they own all the capital in the economy, and their income, the interest rate, R, grows faster than the income of the workers, the wage income of the workers, which is basically driven by the growth rate of the economy, gamma. So for the derivation of his views on capitalism and the economy and inequality, so that ever-increasing returns of capital lead to richer and richer capitalists relative to the workers. Well, for this conclusion, this inequality here is crucial. So in that we have a dynamically efficient economy in our OLG model. Now let's look at more recent episodes. So in more recent episodes, we observed that, well, growth rates are around 1 or 2%, population rate are about around 1% in the United States. So the right-hand side of this inequality here is around 3%. Now let's look at the real interest rate. How do we measure real interest rates in the United States? Well, that's difficult because we have many assets. So if you look at treasury bills or treasury bonds, well, you get something like 0 to 1% in the United States. Let's say 0%. We have inflation of 2%. This means that your real interest rate here on bonds, government bonds in the United States, is -1, -2% nowadays. And if we look at returns on other assets, let's say stocks, we find that the return, of course, after the two crises, the housing crisis, the Great Recession in the year 2008-2009, and the present Corona crisis in 2020, we saw drops of the stock values of 20, 30, or even more, 40, 50% in these two crises. So over the whole period, the real interest rate has been much lower than over the 60s or 70s. So we have something like, if we form something like a weighted average of treasury bonds, stocks, and also housing as a very important asset, well, perhaps we are down to 2 or 3%. And now you see that, well, in this case, real interest rates may even be lower than population rate, the sum of the population growth rate n plus the economic growth rate, gamma. So we have something like R smaller than gamma or gamma plus n more recently. And we might have a dynamically inefficient economy. So this question, whether the real interest rate is higher or lower than the economic growth rate, is a central issue of of economics and has occupied economists, especially growth economists like Robert Solow or Carl Christian von Weizsäcker in the 60s and 70s and nowadays. And it's crucial to determine, well, whether Piketty is right or whether our economy is efficient or inefficient. And you might want to think about these two economic variables, the real rate of return, the real interest rate on the one hand, and the economic growth rate on the other hand, in a little bit more detail. So when we consider policy experiments in chapter 6 and 7 on pension policies and on debt, we make sure that our economy is dynamically efficient and make sure that a change in the policy that also affects savings and hence capital stock is not beneficial by itself just because we have a dynamically inefficient economy. So this concludes chapter 3, and I hope you enjoyed it. If you will take part in my course on Social Security, which consists of chapter 3 and chapter 6, I also encourage you to download the videos on chapter 6 on Social Security, where we derive interest-only results. So for example, that optimal pensions should be less than 20% of gross wages in modern economies, and that pensions, for example, should be paid rather in a lump sum fashion and should not depend on contributions, but paid out more equally among retirees. So thank you for your attention.